We have our own Chuck Dezelah giving a short presentation entitled Double Shot, Observing Two Objects at Once through a telescope, of course. I think the title is fairly self-explanatory. Chuck has been attending our meetings regularly for about the past 3 years and has been fascinated by astronomy since childhood. He's currently our secretary. He has a PhD in chemistry from Wayne State University and works for a Detroit area nanotechnology company. He currently writes a monthly column in the WASP newsletter introducing an object of the month that can be observed in mid-sized telescopes from Stargate Observatory. I have seen him out there checking out objects with a telescope to make sure they're visible and so forth. So he puts a lot of work into that. So without further ado.
Thank you for the introduction, Dale. Appreciate it. I could lower the lights just a little bit. Yeah, so as Dale mentioned, the topic of my talk tonight is double shot, observing two objects at once. So I've always been a big fan of observational astronomy. I love to go out under the night sky and observe either naked eye or through binoculars or through a telescope and try to see whatever it is I can see, glean out any last detail of whatever object I'm looking at. And so it's really a joy and a passion of mine to be out under the sky and look at things. What gave me this idea is that there are a number of objects out there that are famous largely because of the fact that there are really two objects that are near each other. So what we have pictured here is the double cluster, which is in Perseus, which is something that I think most of us, if we've been out and have had a chance to look through a decent-sized telescope at Stargate, have probably looked at the double cluster at some point in time. So the double cluster, I think, is a good inspiration for looking at double objects. People hunt after double stars, so why not double deep sky objects? So the concept is that since visual observing is a great joy to people who love to get out under the stars, why not try to enhance that as much as possible? Deep sky objects are a source of beauty, awe, and wonder for people who love to look through telescopes like I do, and therefore they're very popular targets. And one of the things that you do when you're looking through the eyepiece is using inverted vision, using other techniques to try to just see as much as you can and learn to be a better observer. Since so many astronomers spend so much time, amateur astronomers, probably professionals too, I guess, but amateur astronomers love to get under the sky. Anything that they can do to try to detect a dust lane in a galaxy or see some minor clumping of stars within, say, a globular cluster, that brings a tremendous amount of enjoyment. So if you can combine two objects in one field of view, see two objects at once, that really has kind of a synergistic effect, allows you to really have an extra element to appreciate for the observation. So a few requirements. One of the first requirements of observing a double deep sky object is to have a sufficient true field of view. And I want to contrast a true field of view with an apparent field of view. So one thing to consider is that you have to have you can have a narrow field of view like you have on the left, or a wider field of view like you have on the right. Now, apparent field of view is really whether you're looking through a drinking straw or whether you're looking through a porthole window. So if you have a small apparent field of view, large apparent field of view, it enlarges what you see through the eyepiece, but doesn't necessarily give you more of the sky. Well, it can, depending on the magnification, give you more sky or less sky to look at. So what we see here is the image on the far left and the image on the far right have very different apparent fields of view, but have the same true field of view. So the object that you're looking at, the relative size of it at the eyepiece looks about the same, but it's expanded over that larger area. So you're not looking at more of the sky, but you're seeing something that is essentially like looking at a big screen TV. Whereas the first image and the middle image are having the same magnification, but are actually having very different true fields of view as well, so you're actually looking at more sky. So how do you determine the true field of view? Well, there are actually a couple different equations I found online. One is that the eyepiece field stop diameter divided by the telescope focal length times a factor of 57.3, which I haven't been exactly able to determine where that comes into the calculation. But
that's 180 degrees divided by pi.
Oh, okay. Makes sense to me. So that's, I think, the more exacting way of measuring the true field of view. But one kind of shorthand way that I feel is more field expedient, something that when you're at the telescope and you want to get a quick and good idea of what the true field of view is to take the apparent field of view of the eyepiece and divide it by the magnification. So, for example, taking a look at some of the common eyepiece types that are out on the market, the common colossal eyepiece has an apparent field of view of about 50 degrees. Whereas the super wide style eyepieces, generally eyepieces that are like the Teleview Panoptic, will be about 68 degrees. 82 degrees for things like Naglers, or in this case this is an Explorer Scientific 82 degree eyepiece. And then there are the hyper wides, which can have 100 or 110 degree apparent fields of view. Now, of course, you can calculate the true field of view knowing the apparent field of view and the magnification. So what does this mean in terms of looking through the eyepiece? So if you take your standard 10-inch Dobsonian telescope, you've got a focal length of 1200 millimeters in a typical 10-inch Dob. If you put into it a 50-degree apparent field of view colossal eyepiece, you end up with about a degree of true field of view, so about 1 degree of actual sky that you're looking at with a power of about 48 times. So you get the magnification by dividing the focal length of the telescope by the focal length of the eyepiece, and then from there use the equation that's shown to get the field of view. Now, by going up to a super wide, you can see right away that there's much better framing, that the objects are all having a good amount of background sky behind them, around them, I should say, in order to better frame them, give them a better perspective in the eyepiece. And that only gets better as you go to wider and then wider field of view eyepieces, that you get that extra framing. So you might say at this point, well, this is all nice. It's great that you can have these different fields of view, but why does this impact trying to observe two DSOs, two deep sky objects at once? Well, I mean, in this case, comparing the ones that we just looked at, you can see that there's a considerable difference from one to the other, but in each case, you can see all three objects. But what if you have a different telescope? What if you don't have a Dobsonian reflector? What if you have, for example, a Schmidt-Cassegrain with a much longer focal length, much higher focal ratio? That same 50-degree colossal eyepiece, you can't even see the third galaxy out of the three galaxies that were pictured previously. So here you can see that it frames only two of the three. And that, again, kind of doing that side-by-side comparison of those same four eyepieces, in order to get the same kind of field of view, in order to encapsulate the view that you want to have of all three objects, it requires a considerably wider eyepiece in order to get that same kind of framing of those objects. And then here in this case is the hyper wide. So the having a sufficient true field of view in order to capture all the objects together in one eyepiece view is pretty important. Sufficient magnification to detect both the objects, I think, is also a really important key. It depends on what the object types are. So in this case, we're looking at M46, an open cluster in, I believe it's in Monoceros. And inside of that open cluster is a planetary nebula. And planetary nebulae are usually objects that require a pretty good amount of magnification. They tend to be rather small in angular size. Whereas open clusters tend to be the exact opposite. Open clusters tend to be best appreciated at low power, where they stand out better against the background field of stars. So in this case, there's a little bit of a contrast in terms of the requirement that those two objects might have. So you have to try to optimize that as best as possible. And then the third real requirement is to come up with a suitable list of objects. Some double deep sky objects are relatively common, some are relatively uncommon, and they're reasons for which combinations are more common or less common than others. And knowing what to look for, where to look in the sky, what you can expect to see, and compiling a list of good candidates depending on the telescope you have, the quality of the dark sky that you have, the kinds of objects you like to observe, is really, I think, one of the keys in order to best observe double DSOs. So I divide DSOs into these double DSOs into two categories. You can have homogeneous, in other words, of the same type, two objects that are in the same category, or you can have heterogeneous. So here I've got two images of two homogeneous double DSOs. On the left is an example of what you could call a double galaxy, two galaxies sharing the same field of view. And on the right, here we have two globular clusters, both sharing the same field of view. I want to contrast this with heterogeneous, so having different types of DSOs. And that actually, I think, adds a bit of extra interest, because if you have two very contrasting objects, two objects that are very much differing in appearance, it can really, I think, enhance the experience considerably. So in this case, we have on the left an open cluster combined with a nebula, whereas on the right, there's an example of a galaxy with an open cluster in the same field of view. So with homogeneous, there are only a few categories to consider. You can have two times an open cluster, two open clusters together. You can have two globulars, two planetary nebulae, two bright nebulae together. I'm excluding planetary from that category for various reasons that I won't get into right now, but and then two galaxies. So with heterogeneous, there are many more categories, because obviously there are different, if you take each DSO type and combine them in different ways with all the other types that are available, actually you can get 10 different combinations with the ones that I have under consideration. So with the likelihood, there are three main factors that I want to look at. Is the abundance. So if you have two different DSO types, what is the relative abundance of those two types to each other? For example, are there a lot of examples of that, or only a few? Is it common? Is it rare? And then what's the chance of those two objects being the same part of the sky? Are they likely to exist along the same line of sight? And what's the chance of them being in the same proximity actually in space? So do they occur together? Are they mutually exclusive, or are they going to be actually physically near each other? So the new general catalog of objects actually forms a pretty good representative sample. And you can see that there are more than 6,000 galaxies in the NGC catalog. Compare that to all the other categories, open clusters, globulars, are relatively rare compared to galaxies, but still there are a good number of them. But then you start getting into some of the other categories, and the rarity is definitely apparent. So, looking at the Milky Way edge on, you get an idea of the shape of our galaxy, relatively flat, planar galaxy, and then when you look at the sky, that turns into essentially a band of light that we see across the sky. If we kind of plant that onto a map of the sky, where objects distributed, open clusters are generally located within the plane of the galaxy, so they follow the Milky Way along the sky in a pretty narrow line. Globular clusters tend to be more towards the center of the galaxy, but don't necessarily have to hug very tightly to the plane of the galaxy. Whereas galaxies external to our own would likely not be within the plane of our galaxy. They'd likely be at some high angle relative to the Milky Way plane in order to, mostly because the dust and the stars within our own galaxy would obscure galaxies external to our own. So considering where objects are and why they're there, I think plays an important part in determining the relative abundance or rarity of different object types. So, two open clusters are relatively common, whereas two globular clusters are relatively uncommon. Two planetary nebulae are going to be pretty rare. Two bright nebulae, you have to ask the question, are they really one object, or are they two objects that just happen to be near each other? So that's a little bit questionable about the rarity or commonality of them. Whereas two galaxies, with so many galaxies on the NGC, it's a relatively common event. And then here you can see other categories. I've kind of rated them as common, uncommon, rare, according to whether or not they're likely to appear together, whether or not they're going to be in the same part of the sky, whether or not they're going to, just the likelihood of running across them. So some combinations are indeed quite rare, in fact. So I'm just going to very quickly here kind of give you I guess, a guided tour of some objects that I've seen that I consider to be good examples. Everyone knows about the double cluster, but very few people realize that M35 is actually another example of a double cluster. It's very near 2158 on the NGC catalog. It's a favorite object of mine. You can easily see it from Stargate. You can look at two globular clusters. This one's a toughie though. M53 is easy from anywhere, but 5053 is very loose, very hard to see. It's difficult, but it is an example where you can catch two globulars in the same field of view. Two galaxies. This one's actually one of my favorites. At first glance, you might think it's M81 and M82, but it's not. These two galaxies, NGC 4762 and 4754, are just west of Porama in Virgo. Very easy to find just by slewing the telescope. Two nebulae. Here you have the Cone Nebula and the Hubble Variable Nebula. Can be fit within a single field of view. The Orion Nebula and the Running Man Nebula are close neighbors as well. A lot of people don't realize that. Running Man Nebula is a little tough, but with, say, 10 inches of aperture at Stargate, you can see it. Two planetary nebula. I couldn't really find any good examples of that. The relative rarity of planetary nebulae, and the fact that they're not necessarily tightly clustered, would make them hard to pair up. The open cluster nebula combination is very common. So here's an example of two close neighbors, also within Orion's belt, Running Man Nebula and the Polcar cluster. So I only have a few more here before I wrap up, but open cluster and planetary, I mentioned earlier in 46 with its planetary nebula inside. It's an old favorite, one that's well within the reach of most telescopes. A few people realize that M7, the open cluster in Scorpius, has a nearby globular cluster neighbor. That's going to be a hard one, though, unless if you can get away from the light pollution. One of my favorites, I've seen this from Stargate. The galaxy is tough, but can be seen with averted vision. The open cluster is relatively easy. This is, I think, straddling the Cepheus-Cygnus border, but actually surprisingly doable for a face-on spiral galaxy. Nebula and planetary nebula, didn't really find any good examples of that, unfortunately. Nebula and globular, so the Lagoon Nebula M8 in Sagittarius has a nearby globular neighbor. Again, that might be a difficult combination with light pollution though. Nebula and galaxies a toughie, but globular and planetary nebula, they both tend to be more concentrated near the center of the galaxy because that's where most of the stars are. So that's where more planetary nebulae are likely to be. So here's the Little Gem planetary nebula, which is quite near a globular cluster. I believe that's about 10th magnitude glob. So difficult, but potentially doable. This is a pretty wide pairing, but it's probably the best example I could find of a galaxy and a planetary nebula. Again, that one might be hard to come by though, unless you've got a rich field telescope with a really wide field of view. And then the final object here is one that was a recent object of the month, NGC 6207. It's a galaxy that shares a field of view with M13, the famous globular cluster in Hercules. So just wrapping up here, if you choose your DSOs wisely, you can find that there's a wealth of double deep sky objects. Choosing a telescope with the right focal length to best get the widest true field possible is, I think, a good key to being able to have enough objects that can fit within the range of the field of view to be able to see them. Looks like there's a little bit of lag here. Having low power and wide true field of view, that goes into that choosing the right telescope. Wide field eyepieces can definitely enhance the viewing, allow you to frame objects better and have more targets to choose from. And then, by optimizing the field of view and magnification, you can get the right combination of having enough power for detail and enough field of view to really be able to get good combinations of objects. And with that, I'd like to wrap up and answer any questions.
I'm afraid we're going to have to hold the questions. We're running a little late. So maybe you can talk to Chuck privately during the break.
Could you just show the second slide showing
You
the
do it
first
for me,
formula?
I don't mind. You're just trying to.
We'll take one question. What was it?
Brian, go.
No, I just wanted him to show a slide.
Let's see, so I get the formula down.
The second slide?
I think they had the first formula with
Oh, the formula, okay, yeah, sure.
57.3.
There it is.
Yeah. Yeah, that's it.
Yeah, 57.3 converts from radians to degrees. Angular radians to degrees.
All right. I guess that was
5 times 100.
sort of the question, but
Okay, let's thank our speakers.